when you're looking at problems like these, you might be thinking, well, if the answer is right there on the periodic table, how is she going to test me on this? I could always make up fake elements that you can't look up the answer for on the periodic table. What if we wanted to go the other way? Since we know what the weighted average is, it's right there on our periodic table. What if I wanted you to find the percent abundances instead? How would you do that? Well, your percentages always add up to 100. But because we've been taking our percentages and switching them into decimals, when we add up our decimals, they'll always add up to 1. So if we assign one isotope X, the other isotope would be 1 minus that. So for example, if one isotope is 25%, 0.25, the other isotope is 1 minus 0.25 or 0.75. Now be careful. I've seen some people in the pressure of a test, they accidentally do X minus 1. But no, don't do X minus 1. If you have a little bit of a freak out moment on the test, just put in a basic number like the 25%. Would it make sense for you to do 0.25 minus 1 and your other percentage is negative 0.75? It just doesn't make any sense, right? So 1 minus X, not X minus 1. So I know it looks a little bit different here than what you saw above, but this shows percent times a mass, percent times a mass. They add them up, and then they get a weighted average mass that you can find on the periodic table, right? And that is what we did in the example up above. We're just solving for a different piece of the puzzle. Rather than trying to find the weighted average, we're going to try and find the percentages. It does not matter which one you make the X and which one you make the 1 minus X, as long as you remain consistent. So, what if I make oxygen 16 my X, let's say, and oxygen 18 is going to be my leftovers. So oxygen 16, I'll call my X, and oxygen 18 is going to be the leftovers. So I'm going to do a percent times the mass that goes with it. I'm going to add that to my leftover percentage times my leftover mass. A lot of people will remember this part and then they freak out and go, oh no, what do I set this equal to? And I see people plug in 0 like they're finding a root in math class, or I don't even know, the algebra just gets crazy what they end up doing. Remember that this is the process, percent times a mass, add them up. Your answer is the weighted average atomic mass that you can find on the periodic table. So I need to go to my periodic table really quickly and say, what is the weighted average of oxygen? When you consider all of the isotopes in the world of oxygen, the weighted average is 16.00. Our particular isotopes are 15.9949 and 17.9992, but the weighted average of those guys is 16.00. Now, when you were sophomores, you weren't allowed to use graphing calculators, and you would have had to walk through the algebra to solve for that X. I'm totally fine if you just show me the setup line and then write something like solver and have it solve for you, right? your x, when you go to solve for it, will be 0.99745. And you might be thinking, great, what was x again? Oh, that's right. Up here we said x was the percentage that we're assigning to oxygen 16. It's just right now it's in decimal form. So we need to sig fig round our answer. Our two masses of our isotopes have lots of sig figs. The periodic table mass, this guy only has 4 sig figs, right? The 1, the 6, and then they're both right zeros. So the periodic table numbers are not perfect. If you look at one periodic table number versus another, some of them have 2 decimal places, 3, 4. They're all over the place. So not a perfect number. They count for sig figs. So if I want to keep 4 sig figs, I would chop it right here. The 5 gives that guy a little nudge. So 0.9975. That's it as a decimal. If I were to switch it into a percentage, I'd say 99.75%. Oxygen 16. And then the leftovers, the 1 minus x, 1 minus 0.9975 is 0.0025 in decimal form, or 0.25%, less than 1%, oxygen 18. There's just a sprinkle. Those numbers make sense, right? The weighted average on the periodic table is 16, which means it's a weighted average. It's skewed in favor of the isotope that's more common. So that's why our weighted average is 16 AMUs, because over 99% of oxygen atoms in the world are oxygen 16. And there's only a teeny tiny fraction of them that are oxygen 18. It's a good idea to take that 1 second and see if your answers in the end make sense, to make sure you didn't accidentally typo on your calculator.